Here we are abusing a little bit our privilege as organizers to have our chance to also say our bit. So yeah, the goal, Luis already said it here, is to extend in a way a part of what Ronald Fagin presented yesterday in his keynote address, the last part, when he was giving a formal system for real-valued logics of a very special kind. And okay, let me just put things in a little bit of perspective to help understanding this. Fuzzy logics, or more general, many-valued logics, are the logical paradigm in which one embraces the idea that truth is not always a matter of yes or no, but sometimes it's a matter of more or less true. So truth comes in degrees. Those degrees are typical in some algebraic structures. Sometimes those algebraic structures are defined over the real numbers. And in any case, we believe that the degrees do have meaning, and there have been indeed many works in which the possible ways to giving meaning to those degrees have been studied. But when it comes to the relation of logical consequence using those semantics, in a way, it's a disappointment many times, because it doesn't use the full potentiality of those truth degrees in a sense, because when it comes to consequence, we usually look at the preservation of some special degree, typically the number one, the biggest of the truth degrees. So if all the premises have value one, the conclusion should have value one, this kind of paradigm. This can be changed in a number of ways to make the other degrees play a more prominent role in consequence. For instance, by putting truth constants for each degree in the language, in the propositional language, for example. But more interestingly, recently we have seen this other approach by Ronald Fagin, Fagin-Riegel-Gray, and Alexander Gray from IBM, who have come up with the notion, we saw it yesterday in Ron's presentation, of multidimensional sentences, in which they have sentences in the normal sense of our languages, but they add those sets of tuples of truth degrees that those sentences are allowed to take. And those truth degrees don't have to be necessarily 0 or 1, but also the degrees in between in the real interval. So we are going to take this idea and in cooperation with Ron himself, bring it to another level of language, bring it to first order, bring it to modal languages. We will discuss first the case with the fixed domain because it's easier, and later use it to allow semantics in which the domains of our models will be varying as usual. This will have also a little bit of some finite model theory flavor, because there will be a little discussion about 0-1 laws for those logics. And we will also end discussing what it means for prominent fuzzy logics. So just to recall, Ron already said it yesterday, but this is the kind of axiomatic presentation of a very special kind that he has in this paper with Riegel and Gray for propositional real-valued logics. They have one axiom schema. Those are multidimensional sentences, meaning that here there are normal sentences, sigma 1, sigma k, and then a set of tuples of values that they are allowed to take. In the axiom, we are not saying nothing. We are just saying, well, they can take any tuples. Yeah, and then this is true. Any tuples of truth degrees. And then there are inference rules to manipulate them. For instance, there is a rule that says, well, you can permute those sentences if you permute in the same way the values in the set of tuples S. Or another one that says, well, you can do a kind of a cylindrification if you want. If you have a certain amount of sentences up to k, you can add more from k plus 1 up to n, and then just add more copies of the 0-1 interval. So cylindrification in the usual geometric sense. Or if you have sentences that are supposed to be evaluated in some set of tuples S1, but also in some set of tuples S2, then of course they are supposed to be evaluated in the intersection of those two sets. Several manipulations like this. Let me stress the last one because it's interesting, because it's where the semantics of the whole propositional logic is indeed codified. So everything interesting is actually in the rule number 7 that says, well, if you have a multidimensional sentence of the form sigma 1, sigma k, S, so normal sentences, sigma 1, sigma k of the propositional language, and a set of allowed tuples of truth values for them S, then it could happen that there are already some links between the sentences appearing here from a syntactical point of view. It could happen that some sentence sigma m is made from some other sentences here in the same sequence by combining them using some connective of the language. To be completely general, we write it here with a connective for any additive. But typically, just think of binary connectives if you want, like conjunction, disjunction implication. So you would have one sigma made of two other sigmas, for instance, using some connective. Then the values have to be bound in the same way. No, the values allowed for the formulas inside of this expression will have to be computed using the corresponding interpretation of the connective in the algebraic side of things, and then give the value allowed for the formula in the mth position. So we are restricting the set S to a subset S prime where those restrictions, those links have already been taken into account. Okay, now we are going to do this in the first order level. What can we do? Well, first, as I said, we fix, to keep things easy, we fix just one domain for our models. Let's call it M of any cardinality, finite or infinite. And then we consider M these sentences in which we have to keep track of which domain we are speaking about, because they depend on that as well. You will see it now. The multidimensional sentences are collections of first order formulas, maybe with free variables. Of course, a proof system has to take care of formulas of free variables because it has to be able to take care of formulas of all complexities with their quantifiers. So let's put it like this: phi 1 depends on some variables for phi 1, phi k depends on some variables for phi k. And then what do we have here? In S, we will not have any more just tuples of truth values, because now those formulas having free variables are not univocally determined from the semantical point of view, because when we change evaluations of those variables, we will get different truth values. So actually what we will want now will be functions from tuples of the individuals in the domain to truth values in 0, 1, by allowing these variables to be instantiated in different ways in the domain and always taking some truth value in the interval. So that's the kind of thing we have now, tuples of functions, not just tuples of truth values. Of course, if those formulas are actually closed, they don't have free variables, then it all boils down to what we have in the propositional case. There will be no need to have functions, and there will be no need to speak about the domain in this notion of empty sentence. So an example, just to fix ideas, you will see it very clearly. Imagine I have a multidimensional sentence just with two first order formulas here, pi px and for all x ux. So you see, one has a free variable, the other one is a sentence, doesn't have any free variable. Then what should I put in my S here in this set? I should put tuples of functions. But in the first case, I need a function with one argument. So I need functions that go from M to 0, 1. And in the second case, I don't need a function. I just need constant values because here there were no free variables. So maybe I could just put this restriction that it's a value between 0.5 and 0.8, for instance, whatever you want. So this is the kind of stuff we are going to have. Okay, this fits well with the normal semantics of many-valued first-order logics in the following sense. How do we interpret in a model first-order formulas? So maybe we have a model with a domain M. Well, atomic formulas of the form a predicate P of whatever additive applied to some members of the domain, it's interpreted typically by using a function for this predicate symbol, a function that takes values on 0, 1. So you see, it's the kind of thing. The function appears already in the atomic level. Then when we go to more complex formulas, we just define it inductively. We want to know the truth value of a formula obtained by using some connective circle, whatever connective, conjunction, disjunction, etc., of any additive. We just use the truth values of the formulas inside and operate algebraically with the function, say the algebraic operation corresponding to this connective. But the interesting bit, of course, we are in the first order language, is what we do with quantifiers. The typical idea has been, still is, in all the works in this area, to interpret the universal quantifier as the infimum of the truth values of the instances of the formula inside, and dually the existential as the supremum of the truth values of those instances. We have no problem doing this because we have a semantics of 0, 1, so all infimum and suprema are defined. Now, in this sense, you see that we do obtain for each formula with three variables a function from n tuples of the domain, if there are n free variables, to 0, 1. So we can say that any formula defines a corresponding mapping in the model. And those were the mappings that we mentioned in our notion of empty sentences. So now it makes sense to say that the model satisfies an empty sentence if whenever we take the mappings defined by the formulas here, by the phi's, this gives us a tuple in the set S of allowed tuples for those formulas. Okay, so we have to take Fagin's and other axiomatic system and just lift it to the first order level. We can do it in a rather straightforward way. So the axiom will look exactly as the same. So we put here all possible tuples, and then of course for any formula this is going to be trivially true, so it's an axiom. And the rules have just the obvious modification, so it's essentially the same kind of thing, but written for first order formulas, the permutation, the cylindrification thing, etc. What happens with interesting rule number 7 that I stressed before? Well, this becomes a bit trickier because now we have to take care of more ways in which formulas can be built. Okay, the first possibility, remember, this was the idea of having formulas with set S and restricting to the set S prime in which we have already taken into account the possible links that these formulas have, one with respect to the others. So if the link is given just by using a connective, then we apply the same connective to the corresponding functions, no surprises here. But if the link is given by taking a quantifier, so if it is the existential quantifier, we have to apply the supremum to the corresponding function. If it is given by the universal quantifier, we have to apply infimum to the corresponding functions. And then that's what we obtain in our conclusion for this rule. So we have a new axiomatic system of this very special kind for empty sentences, now at first order for a fixed domain, and we managed to prove the corresponding completeness theorem. Whenever we have a finite set of this kind of beasts, this kind of empty sentences, so a finite set gamma and some small gamma empty sentence to play the role of conclusion, then the small gamma follows from the big gamma in this proof system, even if it is a consequence in the semantical sense of this set of premises. And we can prove this theorem by using the same trick that Fagin and others were using in the previous paper, which was a syntactical manipulation of the set of premises until converting into just one sentence equivalent that you can easily see to have the small gamma as consequence. Now, how does this look for particular logics, well-known logics in the fuzzy world, like Recursivity, product, Gödel, predicate logics? If we restrict to the language without equality, we can obtain the completeness theorem for them, and a standard completeness theorem because this is the semantics over 0, 1. To do that well, because we have to restrict to just models over one domain, so we have to have the way to get to just one domain. So we pick a countably infinite domain. And we just play with Levenheim's column theorems, which we proved in the previous work in 2016 with Pilar de Lunda and Angel Garcia Sardagna, that tells us that if we have phi 1, phi k first order sentences, and we have some prescribed real values for them, R1, Rk, we can always find a model with a countably infinite fixed domain in which those formulas take the exact values that we wanted. Yep. So this allows us to use our general completeness theorem that we have just seen to write how it would look when the consequence is just the consequence of having value 1. We can just write it. Phi 1 takes the value 1, phi n takes the value n, implies that the psi takes the value n in our proof system, even only if this entailment is true in the usual form of entailment. How this is related to the existence or non-existence of a standard completeness theorem for those logics will be discussed in the end of the talk. Now, let me just tell you very quickly that the same thing could be done in a modal language instead of a first-order language, just by using obvious modifications. We would be speaking of a semantics based on a crisp Kripke frame, meaning that we have a normal accessibility relation or a classical accessibility relation between worlds, and just write everything for model formulas in this multidimensional fashion with the corresponding modification of rule 7 to take care of formulas obtained by the necessity or the possibility operator. And we would have, again, a completeness theorem for that. Now I leave the space for Guille to continue.
All right, thank you, Carlos. So then, so the next slide is just stating that we indeed get a 0-1 law when instead of regarding the full interval from 0 to 1, we just take some finite subalgebras from that subinterval. For example, in the talk by Javier Caicedo of joint work with us, he presented several examples of these finally valued logics, such as finally valued Lukashevich logics or Gödel logics, and also Amanda in her talk mentioned these things as well. So what we can get by the same techniques that Javier was explaining in his talk of translating basically these many valued logics into classical first order logic by adding predicates, unary predicates to represent the truth values and using Overshelf's version of the 0-1 law, we can obtain a 0-1 law for this kind of subset of multidimensional sentences essentially here. And we get that basically on finite models, a multidimensional sentence is either almost surely satisfied by all finite models or almost surely not satisfied by all finite models. And then can we go to the next slide? Yeah. So I think that that's pretty much that. So now the next question, right, besides the 0-1 law, because that 0-1 law still is restricted to sort of the logics for sort of fixed domains, let it be finite or infinite. But the next question would be, well, what happens with the logic of all domains? No, after all, traditional first order logic is not really restricted to one single domain, but rather is the logic of all possible domains. And in this case, what we could ask, intuitively speaking, when we ask this question, we could ask, well, if we consider the logic to be just a set of inferences, let's call it like that, where on the one hand, we have all the premises, let's say a set gamma, and then on the other hand, we have a conclusion, and we consider a logic to be the set of all such inferences that the logic consider to be valid, no, to be something that can be provable in the system. Well, we might ask, if we look at the intersection of all those inferences for every single domain, let it be finite, infinite, whatever, what is left in there? How can we axiomatize that? Well, if it is the intersection of all these inferences for every possible domain, obviously it cannot contain any multidimensional sentence that involves any explicit mention of a domain, right? Because if we would contain that, then it could not be in the intersection of all of them, because these domains, they don't need to be they could be disjoint for all we know. So then what is left in that intersection? Well, clearly that would be multidimensional sentences like in here, such that the side of the multidimensional sentence that contains traditional first order sentences only contains first order sentences rather than first order formulas, sorry, right? So when we restrict ourselves to multidimensional sentences that only contain first order sentences, to be a little bit redundant, then the logic that we are trying to axiomatize will contain only sentences of that kind, precisely because it's going to be in the intersection of all of these other logics, to call it somehow, of a specific domains. And in fact, for these kind of multidimensional sentences, even if the language contains equality, before we were restricting ourselves to languages without equality. I mean, we could have them, but it's just that the Lewis-Hammerskoellen theorem that we used before doesn't work for languages with equality for obvious reasons. That only works for languages without equality. But then, of course, with languages with equality, we know, and this is a general Lewis-Hammerskoellen theorem for all, pretty much for all many valued logics, that in fact, if a sentence has an infinite model, it will have a countable model too. Of course, obviously, in a countable signature. We are thinking about the countable signature here. And in fact, what this tells us then is that to solve our problem of axiomatizing this logic of the intersection of all the things, we could restrict our attention actually not to all domains, but if we just consider all the finite, or at least good examples of all the finite domains, right? Sort of in such a way that they will be pairwise disjoint. And one example of a countable domain, that's all we really need to care about. So in the way of trying to axiomatize this logic, what we could do is that we could introduce the notions that we saw before for a fixed domain. We could introduce them instead for this collection of legal domains simultaneously. So what would that mean? Now, the sort of like, let's say, like in Moshe Vardi's talk, he was saying how, well, formulas basically define a query on a given structure. Well, you could think about these formulas defining a fuzzy query, in a sense, on what domain? Well, the union of all the legal domains, essentially, right? So that would be the idea. And then what we are saying basically is that, well, in a multidimensional sentence, that given multidimensional sentence is going to be true if all these formulas that we have open here, they are going to define respective fuzzy queries on this union of all the legal domains that belong to in some kind of tuple that lives in this set S that we have here. And then we can move to the next. And then, of course, respectively, what we do is that we modify the axioms to account for this, where before we had one fixed domain, now we are going to have the union of all of these legal domains instead. Everything else is rather straightforward. So we are just including that union, replacing the union for the legal domain. And now the only difference is that, in fact, when we look at rule 7, I mean, you could not see this because we have not said it, but and it was not perhaps so clear in Ron's talk, but the whole purpose of rule 7, really in the completeness proof, is to produce a model. Rule 7 is going to give us a way to define a model of something, right? Like you, at some point, you want to create a model of a certain sentence. And in fact, in our previous version, that model, we knew how we could build it because the domain was fixed. So you knew it would have to be something that you would interpret on that fixed domain. But here, all we need in order to find that model is to find one of the legal domains such that you can define the model on that particular one, right? So if we find one, that's sufficient. We don't need to find a model in every legal domain. It's sufficient to find one legal domain where you are going to do that, because then in the completeness proof, that's all you actually need, right, in order to build the model. And then we have this reformulation of rule 7, which is essentially the same as before, except that now we are quantifying existentially over this M. And then we can go to the next slide. And then, well, what we get is essentially this result, no? That, well, in fact, in our system, I mean, if gamma is finite, and there is a good reason for this kind of restriction, which is that, for example, since this applies to every possible real value logic, essentially on the interval 0, 1, in the case of Lukashevic's logic, this is known on the standard semantics that we are using, this is known not to be complete when gamma is an infinite set of sentences in general. So we have to be careful. We have to add this restriction that gamma is finite. And then we have this completeness theorem that, well, it axiomatizes the logic of all legal domains, to put it somehow. No? And then similarly, of course, we can capture now the logics, including equality, of all these traditional famous real value logics, such as Lukashevic's product, Gödel, and so on. All of them can be captured in our system in this way. This is analogous to what Carlos was presenting before. It's just that now we are capturing the logic of all, I mean, the logic containing equality, whereas before we were not able to capture the logic containing equality because of the failure of the Lewis-Hammerskoll theorem that we used before. All right, so then we go forward. Now, importantly, this system is a little bit strange because, of course, we know that validities in Lukashevic's and product logic, these are not recursively enumerable. This is of all results by Scarpellini, Hayek, and Montagna. And we also know that in the case of the modal logics, Amanda presented her result that, in fact, there are also global consequences. I mean, finitary global consequences also not going to be recursively enumerable. So we have a similar kind of phenomena. And now, importantly, then you might ask, well, okay, so you know this, and at the same time, you seem to be axiomatizing this logic. So what's going on here? Well, recall that, in fact, the fundamental purpose, in a way, of a completeness theorem is to turn a universal statement, right, into an existential one about the existence of some kind of proof. So basically, we want to, for example, in the standard case of first order logic, we want to obtain a sigma 1 claim on the natural numbers, right, when our system is arithmetizable. But of course, Bukashevich and product logic, they are not recursively enumerable for validity. So obviously our system could not be recursive, right? It's not arithmetizable, just because otherwise we would be contradicting these classical results. So what's going on? Well, in fact, Fagin already gave a little bit of a hint of what was going on during the talk with Ron. And he mentioned that, well, in fact, there is a sort of hidden infinitary logic in these sentences that we are using here. And that is true in the sense that if we were to interpret this system in set theory, we would need to use the same kind of technology that we would use to interpret infinitary logic. And in fact, it's so bad that unfortunately, rule 7 itself is not going to be deciding whether the set S prime in rule 7 is empty. This is not a recursively enumerable problem, right? So in fact, you can quote there the problem that, satisfiability in a countable domain. And then what we obtain, in fact, is a system that is not finitistic in the sense of metamathematics, right? In the sense of cleaning. This is certainly not a finitistic system because it has this sort of infinitary flavor to it. However, it still has a finitary presentation, which is quite interesting because the axiomatizations that were in the literature for these logics before, first of all, they were not one fitting all of them, like in the case of what we have presented here, but also they were infinitary axiomatizations in the sense that they had infinitary rules, whereas we do not really have an infinitary rule. But of course, you could make the case that perhaps checking that S prime is non-empty, in a sense, this is kind of an infinitary rule, no? Because you have to do an infinitary process in many cases, no? If you are dealing with some domain that is countable or something like this, right? You might have to do an infinitary process, complete an infinitary process. But it's still interesting. And moreover, we have axiomatized more levels of reasoning than just preservation of one. And with that, I'm going to finish because we are out of time. Thank you very much.